Hi, Algebra 2 honors people. So, real quick, let's recap what we did yesterday in class, because I think we kind of ended fast. So, real quick, we were on page 45 in your notes packet. We were talking about multiplication of complex numbers, so two numbers in the form a plus bi. And the paper started by saying, let's plot 3 plus I, 1 plus 2i, and its product, their product 1 plus 7i. They didn't tell us how they really got that information. We will deal with that in a moment, but real quick, let's talk about again what the graph is telling us. So we plotted 3 plus I, and we figured out that the angle between the positive real axis and 3 plus I is 18.43 degrees. And remember, we got that because we considered, what if we had this little triangle with 3 units on the base and it was 1 unit tall, and I wanted to know what this angle was, and the right angle was over there. We said that the tangent of this angle theta is equal to 1 over 3. We used inverse tangent on our calculator of 1/3 to get our degree. Again, make sure you are in degrees. There are other forms of measuring angles on the calculator that we will get to later. But for now, degrees. We figured out that we had 18.43 degrees there on that 3 wide, 1 tall triangle. On this 1 wide, 2 tall triangle for 1 plus 2i, we got a 63.43 degree angle. And then when you multiply the complex numbers together, you get this as your result, 1 plus 7i. Its angle is 81.86. And the last thing we figured out before we ended class was, what do you notice about the angles? This is number 4 on this page. What do you notice about the angles? The angles of the factors, so the two things that multiplied to get the product, the angles of the factors add to give the angle of the product, the answer. So, multiplying with these complex numbers, it isn't just this random algebraic thing. On the Argand plane, it figures out the angles. So this starting angle with this other starting angle, add them together, you get the final angle. Now, part 5. This is the part we did not quite get to in class. So, number 5. Find the modulus of 3 plus I, 1 plus 2i, and 1 plus 7i. Now, what the heck is a modulus? This is a word that means find the length of the segment from the origin to that point on the Argand plane. So, I'm going to go back to this idea of triangles. Let's take this little guy for example. If I have 3 as a leg and 1 as a leg, I just need the Pythagorean theorem to figure out that third hypotenuse leg. So what I would do is I would take, let's do this guy over here, I would do 3 squared plus 1 squared is supposed to give me c squared, which is my hypotenuse. In this moment is going to be my modulus of that complex number, 3 plus I. So doing that, I figure out that c, the modulus, must be the square root of 10. Going to the next one, I have 1 plus 2i. I'm going to do the same thing. I want to know what is the length of that black line on this little triangle if it was 1 wide and 2 tall. So I have 1 squared plus 2 squared is supposed to give me c squared. And I figure out that my modulus on this guy must be the square root of 5. So then, my final one, my answer, I have 1 plus 7i, so to get my modulus, I'm going to do 1 squared plus 7 squared is c squared, which tells me that my modulus on this guy must be the square root of 50. So find the modulus of each of these. There we go. Let me highlight those so we can see them. So I multiplied two complex numbers to end up with a complex number. But what do you notice about the modulus of each of these? I'm pretty sure the plural would be moduli. So what do you notice about the moduli here? And hopefully you see that if I take the 2 moduli that I was multiplying to begin with, I get my answer. So the square root of 5 times the square root of 10 is the square root of 50. Because when I'm multiplying square roots, I can just bring them together inside one radical. So that's how I get the square root of 50. So all of that to tell us when we multiply complex numbers, two things are helpful and are happening here. So the angles of the factors add to give the angle of the product, and the moduli of the factors multiply to give the modulus of the product. So those are our two conclusions from working with the multiplication of complex numbers. The angles of the factors add to give the angle of the product, and the moduli of the factors multiply to give the modulus of the product. Now, real quick, while we're on this, let's talk about how they actually did this multiplication, because we still haven't seen that yet. Hopefully, when you look at this right here, you see that it looks very similar to what we were doing with quadratics and factoring. Now, clearly, there's no x here, but I have a number that is connected with addition, so two terms, multiplied by another set of numbers connected with addition. So I'm going to FOIL these to get my product. So let's see what that looks like. I'm going to scoot the page down a little bit. And real quick, this video is on my CASA website under the Algebra 2 Honors Assignments. If you want to go back and look at anything and slow down the video, rewatch something, please feel free to do that. Let's watch it through here right now just so we can get through everything. But if you want to rewatch it, please feel free to finish up your homework today and tomorrow. So let's finish multiplying here. So I have 3 plus I multiplied by 1 plus 2I, and I am going to FOIL. So going one by one, first outer, inner, last. 3 times 1, I get 3. 3 times 2I, I get 6I. I times 1, I get 1I. I times 2I, I get 2I squared. But I can clean that up. I see some like terms. First off, 7I. 2I squared, I know, is negative 2 because I squared is equal to negative 1. Lo and behold, there I have my 1 plus my 7I. And that's your final answer. So just FOIL it out, and then whatever powers of I you see, just make sure you simplify it down the whole way so we have a single power of I. That's multiplication by complex numbers. We add the angles, we multiply the moduli. But let's take a look, and the back of this paper is blank, so let's take a look. What if we were dividing? And we're going to use those same numbers actually. So we're going to do the 3 plus I divided by, no, the other way? Let's do the other way. 1 plus 2I divided by 3 plus I. Let's see what happens there. Make sure I get this right. 1 plus 2I divided by 3 plus I. So, dividing, let's real quick make some predictions. If with multiplying I added the angles, I have a strong hunch right now I am going to subtract the angles to get my final answer. And if I was multiplying the moduli to get the modulus of the answer, I am thinking I'm going to divide the moduli to get the modulus of the answers. So let's see what happens. First off, I know that the angles of these two, flipping back to the front real quick, 1 plus 2I has an angle of 63/43. I'm suggesting we subtract them, subtracting 18/43 right there, which would give me a nice 45-degree angle. And I'm suggesting we divide the moduli. So the modulus of 1 plus 2I was the square root of 5, and the other was the square root of 10. So that would be the square root of 5 divided by the square root of 10, which I can simplify to the square root of 1/2, 5 divided by 10. So that's my guess right now. Let's see if that ends up being true. So this is just a guess for the time being. Now, how we divide these is a little bit different than when we multiply, add, or subtract. Adding makes sense. You get like terms. Subtracting, it makes sense. Watch your negatives, add and subtract like terms. Multiplying is not even that hard. We saw with multiplying on the front here. We just have to FOIL, and it's no big deal. Simplify the powers of I where we need to. Now with dividing, it's a little bit different, and it's trickier because I have a sum divided by a sum. Now division does not undo addition. Division undoes multiplication. Subtraction undoes addition, but division and addition do not undo each other. So at this moment, I am not allowed to divide like 1 by 3 and 2i plus I. I'm not allowed to do that because of the addition in there. So what I'm going to do instead is use what we are going to call the complex conjugate. Now, the complex conjugate helps us turn imaginary complex numbers into real numbers. It does that using the difference of squares, which we have already factored. So here we go. I'm going to focus on the bottom. 3 plus I, its complex conjugate is 3 minus I. So the real part and the imaginary part stay the same, but the sign in the middle changes. If I FOIL this out, let's see what happens. I get 9 minus 3i plus 3i minus I squared. The 3i and negative 3i completely cancel each other out, which is fantastic. Negative I squared, I know, is going to become positive 1. I squared is negative 1. It was already subtracting, so I get a positive 1. So I get 10, a nice, delightful, real number, no imaginary part to it at all. So complex conjugates, if you FOIL them correctly, will always result in a real answer. A solid, real, no imaginary part answer. So here's what I'm going to do. If I can create a denominator that just has a real denominator, not a sum of a real and an imaginary, but just a single denominator, then I'm able to divide a sum on top, divide it, divide it. So let's see how that looks. I want to do 1 plus 2i divided by 3 plus I. What I'm really going to do is just multiply by 1. I don't want to change the value of this quantity. If I multiply by 1, and I literally like to draw this giant 1 so I don't forget, that's what I'm doing. I am multiplying by 1. That is all that I'm doing. But what does that 1 look like? In this case, that 1 is going to look like the complex conjugate divided by the complex conjugate. Just like 5 divided by 5 is 1. 2 divided by 2 is 1. A complex conjugate divided by the complex conjugate is 1. So I'm going to do 3 minus I divided by 3 minus I. That equals 1, but now I'm going to FOIL on the top and the bottom and see what I get. On the top, I get 1 times 3 is 3. 1 times negative I is negative I. 2i times 3 is 6i. 2i times negative I is negative 2i squared. In my denominator, we already did this work right up here. I know my answer is going to be 10. So that's handy. Now I'm going to simplify this up here. I get 3 plus 5i plus 2, because the I squared becomes a negative 1. That's all over 10. So I get 5 plus 5i over 10. Now, because I have a sum divided by one thing, it's like I can divide both pieces. It's like I'm multiplying by 1/10 almost. So if I divide this out, divide it here, I get 1/2 plus 1/2 I. So dividing this guy here is the same as this. These are equivalent in quantity. So let's prove that. Our guesses right now were that if I was dividing with these two, their angles are going to subtract, meaning the answer should have a 45-degree angle. And I should divide the moduli, so the modulus of this guy is supposed to be the square root of 1/2. So let's see if that happens. Down here, I'm just going to draw another Argand diagram quick. If I were to graph, if that's 1 and 1, 1/2 and 1/2 would be here to here. I'm looking at this point right there. Now let's think this through. If I have a triangle with 1/2 on the leg, 1/2 on the other leg coming out of the right angle, I know for a fact this is a 45-degree angle, because it is an isosceles triangle. My picture's a little bit off, but just we know that this is a 1/2 on this edge, 1/2 on this edge. It's a 45-degree angle because this is isosceles. So our prediction that we just subtract the angles that we were given, this subtract this, I get 63.43 minus 18.43, which is a nice 45-degree angle. So that is confirmed. Hooray. The second thing is, what's the modulus? So now I just want to know what's the length of this segment right there. So I'm going to do the Pythagorean theorem again. I would do 1/2 squared plus 1/2 squared is supposed to be my modulus squared. I get 1/4 plus 1/4 is equal to c squared. That's 2/4, or 1/2 is c squared. So lo and behold, c, my modulus, is the square root of 1/2, which is what we predicted earlier. Dividing the moduli would just be the moduli of 1 plus 2i divided by the modulus of 3 plus I, square root of 5 divided by the square root of 10, which is the square root of 1/2. And that's what we got just there. Hooray! So we have now done all of the regular operations with imaginary numbers. We can add, subtract, multiply, and divide. Adding and subtracting, just a matter of finding like terms. Multiplying, we know we can distribute as we need to. Whether we're doing something as complicated as 1 plus 2i times 3 plus I, or if it's a little bit simple, if I just have 5 times 1 plus 2i. We just have to distribute. Just follow our distributive property. Division is the most complicated, but all you need to do, it just comes down to multiplication. Multiply by the complex conjugate, top and bottom, because that's just giving you a 1. Really, you're just making an equivalent fraction here. You did this back in like 6th or 7th grade algebra, where you were making common fractions. If you needed, like let's say I wanted, let's do 3/4 was the original fraction, but I wanted it to be, let's say I wanted it to be 20 as my denominator instead. You didn't just multiply the 4 by 5 to get there. You had to multiply the 5 on the top and the bottom to get that 20. So if you multiply by 5 on the bottom, multiply by 5 on the top, you get an equivalent fraction. Even though it looks different, it is equivalent because all you did was multiply by 1. That's what we're doing here. We're just picking a very specific thing to multiply by. So at this point, please take a look at your homework for today. You're able to do everything that I'm about to say. It's in your textbook on page 250 to 251, and we're going to check this on Thursday. So not Wednesday. Wednesday is career stuff day, but Thursday. I would like you to try 18, 22 to 34 even, and then 48 to 50, all of those. 54, 56, and 65. Take a look at those. You're able to do all of those operations now. And again, it all comes down to your answer should be in the form A plus B I. Real part, imaginary part. Either of those is allowed to equal 0, but you only want I. Single I, no exponents on the I other than 1. So that's going to be your final answer for each of these. It could be real only, it could be imaginary only, but that's the complex form. So have at it. Good luck. If you have any questions, please write them down and we can talk on Wednesday. And this homework assignment is due on Thursday. Bye, guys.